I go now a basic idea about acids and bases. We define the types of acid. We describe Arrhenius acid, Arrhenius bases. Also, we talked about Bronsted-Lowry acids and bases, which are based on proton transfer. Acid, Arrhenius, Bronsted-Lowry bases, acids, Bronsted-Lowry acids are proton donors. Bronsted-Lowry bases are proton acceptors. So we look into some of the ideas, acid dissociation constant, K sub A value. And we also talked about pK sub A value. There are two ways to indicate ionization constant, acid ionization constant. One is to K sub A value, other one is pK value. Bases also have K sub B values and K sub A values. So today we're going to go over properties of acids and bases. All right. Let's go to the all right. Now we're going to look at neutralization reactions. We're going to talk about this little later in more detail. Neutralization reactions are acid-base reaction to neutralize each other. So we will discuss in a few slides from here. First, we're going to look into metal reactions with acids. The equation below, magnesium react with strong acid to give hydrogen. This is a single displacement reaction and also a redox reaction. Strong acid react with certain metals, and those metals that react with strong acid are called active metals. They produce magnesium chloride with HCl, magnesium chloride, and hydrogen, as given in this equation. If you look at this reaction, reactions in solution could be written as net ionic equation. So net ionic equation for metal reaction is strong acids are given below. So this is an oxidation reaction, oxidation reduction reaction, redox reaction. So based on metal reactions, we come up with the activity series for metals in their tendency to reduce aqueous solution, get reduced in aqueous solution. They reduce hydrogen ions to hydrogen. So these active metals are in a series is listed below. The reactions between strong acid and the metal take place, and the metal ions are oxidized. Hydrogen ions are reduced. So this ability of reduction of protons to hydrogen is the most on the top of this activity series. Lithium is the most reactive. And as you go down, you can see the reaction are less reactive, and in here, fourth one from the bottom, the hydrogen is the one that is shown as in a reduction reaction, oxidation reaction. What in fact take place is reduction of this reverse of these. These are half reactions. We talked about half reaction. So metals below hydrogen here are not reacting with, do not react with aqueous metal acid, strong acid. So we can come up with this idea that reduction of protons, so hydronium ions in solution produce an activity series. So we also going to look into other reactions. The other reaction we're going to look at is reaction with metal hydroxides with acids. Acids react with metal hydroxides like KOH. This is a neutralization reaction to produce water and the potassium chloride. For this also we can write down total ionic equation and net ionic equation. So this is the total ionic equation. When you remove spectator ions, neutralization reaction is basically hydrogen, hydronium ion plus OH ions producing water. So some of the things we learn in solution chemistry, aqueous solution, applies here for acid-base reaction. Now we're going to look into more reactions of acids. Acids also react with metal oxide, like they do with metal hydroxide. Metal hydroxide behave as a base and just produce metal, the salt, like given here. Water is produced, and the ion, calcium 2 plus ion, calcium oxide goes to calcium 2 plus ion. This is net ionic equation. So you can fill up the missing anion for hydronium ion, like hydrogen chloride, would produce calcium chloride and water. Metal oxide also behave like a bases towards acids. Metal acids also react with carbonates and bicarbonates. We talked about acid reaction with hydroxide, metal oxide, and now carbonates and bicarbonates. When acid react with carbonate and bicarbonate, they produce carbon dioxide and water, as indicated in the equations here. The first is the total ionic equation. The second one is the breakup of carbonic acid produced into carbon dioxide and water. The total ion equation is at the bottom. Acids react with carbonates to produce carbon dioxide and gaseous carbon dioxide and water. Since carbon dioxide gas is produced, these reactions go to completion. Therefore, as carbon dioxide is removed, all carbonates will be converted to carbon dioxide and water. Strong acid reacts similarly with bicarbonate. Now bicarbonate goes to carbonic acid with acid, and carbonic acid will be breaking down to carbon dioxide. Similar reaction. So acid reacts with carbonates and bicarbonates, producing carbon dioxide and water. Acid also reacts with bases like ammonia and amines. Ammonia and amines are bases which are based on nitrogen. Any acid stronger than ammonium ion is strong enough to react with ammonia to give salts. Ammonia produces ammonium ions. Therefore, anything that is stronger than ammonium ion will react with ammonia to produce salt. So hydrochloric acid, HCl, react with ammonia to produce ammonium ion and chloride ion, ammonium chloride. This is a Bronsted-Lowry acid-base reaction. Proton transfer takes place from HCl. HCl is proton donor, and ammonia is proton acceptor. The amines we are not going to talk about here. Amines are compounds where the ammonia has alkyl groups. For example, NH2CH3, methylamine. There's a CH3 group in the ammonia, replacing hydrogen. So amines are discussed later in chapters. We are not going to cover about that. So acid reaction with ammonia and amines are similar. For example, methylamine with HCl to produce, just like ammonium chloride, methylammonium chloride is produced. Now we're going to talk about self-ionization to describe the pH of water solutions, aqueous solution. pH is based on hydronium ion concentration, and pOH is based on hydroxide ion concentration in water. First, to understand pH and pOH, we have to understand the self-ionization of water. Pure water react with another water molecule to produce hydronium ion and OH ion, according to this equation. One water molecule acts as an acid, Bronsted acid, Lowry acid. Another water molecule, which is in the red here, base, accept a proton, go to conjugate acid, base conjugate acid, acid conjugate base. Water, OH is the conjugate acid conjugate base. Water and hydronium ion is the base conjugate acid pair in the Bronsted-Lowry reaction of two water molecules. This is an equilibrium reaction, which is more towards water side, more favored towards reactant side. So we can write a ionization equilibrium constant, or Kw. Ionization of water is called equilibrium for ionization of water is called Kw. It's also called ion product of water. Kw is the equilibrium constant for self-ionization of water. Kw is product of, when you write down the equilibrium constant, two waters disappear on the reactant side. Therefore, product of the OH concentration times hydronium ion concentration. In neutral water at 25 degrees Celsius, there are 1 times 10 to the negative 7 hydronium ions and 1 times 10 to the negative 7 hydroxide ion concentration. Therefore, if you multiply 1 times 10 to the negative 7 times 1 times 10 to the negative 7, product became 1.0 10 to the negative 14, as shown here for Kw at the bottom. So this is a very important idea for defining pH and pOH of aqueous solutions. In pure water, hydronium ion and OH ions are formed in equal amounts. As shown in the balance equation for self-ionization of water in the previous slide. This means pure water has 1 times 10 to the negative 7. Product is 10 to the negative 14. In pure water, hydronium ion and OH ion are equal. Therefore, to produce 10 to the negative 14 Kw value, hydronium ion concentration in pure water has to be 1 times 10 to the negative 7. And the OH also same concentration. The equation of ionization of water applies not only to pure water, but always also to any aqueous solution. Even the acidic basic solution, this Kw is same, but the relative amount of hydronium ions and hydroxide ions going to change depending on what we added to the water solution. The product of hydronium ion and OH ion in any aqueous solution is 1 times 10 to the negative 14 ion product of water. For example, if we add 0.010 mole of HCl to 1 liter of pure water. So when you calculate the hydronium ion concentration, HCl breaks up completely to hydronium ion, therefore produce for 1 liter 0.010 mole of hydronium ion. Therefore, hydronium ion concentration is 1 times 10 to the negative 2. 1 times 10 to the negative 2 hydronium ion concentration. Now, hydronium ion concentration is mainly from strong acid. Therefore, it changed the hydronium ion concentration from 1.10 to the negative 7 to 1.4 times 10 to the negative 2. This means the concentration of hydroxide ion is 10 to the negative 14. Why? Because the product of hydronium ion concentration times OH ion concentration has to be equal to Kw. Therefore, Kw divided by 1 time 1.0 10 to the negative 2. Kw is 1 times negative 14 divided by 1 times negative 2 is 1 times negative 12. Therefore, adding acids and bases to water solution change the concentration of hydroxide and OH, hydronium and hydroxide concentration. But their product, hydronium ion and hydroxide ion product, is going to be 10 to the negative 40. So having this idea, Kw and hydronium ion concentration of water or hydroxide ion concentration of water related by Kw, we come up with the idea about pH and pOH. Because hydronium ion concentration for most solution are numbers with negative exponent, we commonly express these concentration as pH. You notice that hydronium ion concentration in water is 10 to the 1 times 10 to the negative 7. We try to change that to a number we can handle. So we change hydronium ion concentration, for example, 10 to the negative 7, 1 times 10 to the negative 7. Take a log of that. Log of 1 times 10 to the negative 7. If you plug in 1 times 10 to the negative 7 in your calculator and press the log button, you get minus 7. To change to a positive number, you multiply after taking log, multiply with the negative sign, pH becomes 7. So definition of acidic and basic solution in terms of pH. So water, neutral water without acid or base is hydronium ion concentration is 1 time negative 10 to the negative 7. When you take the pH becomes 7. Neutral water has pH of 7. When hydronium ion concentration increase, therefore negative 7 is the neutral. As it increase, it becomes negative 6, negative 5, negative 4. The pH of acidic solution is less than 7. Basic solution is greater than 7. Therefore, this acid ionization ion product of water, Kw, gives us a convenient way to indicate the acidity or basicity of water, aqueous water solution. Neutral solution pH is 7. Greater than 7 is basic. Less than 7 is acidic. You already knew about it, I assume. Let's look at examples of pH and pOH calculation. Just as pH is a convenient way to designate hydronium ion concentration, pOH is a way to designate concentration of OH ions. Sometimes we use pH, sometimes we use pOH. pOH is similar to pH, hydroxide ion concentration taken the log and change sign become POH. POH is a neutral solution, is also 7. Because Kw is 1 times 10 to the negative 14. Hydrogen ion concentration is negative 7. OH ion concentration should be negative 7 as well. So take the logarithm of 10 to the negative 7, become POH is 7 also. For neutral solution, pH is 7, POH is 7. Therefore, sum of the pH and pH of a water solution is always equal to 14, just like 10 to the negative 7 times 10 to the negative 7 is equal to 10 to the negative 14. If you take the log of Kw, change sign, you also end up with 14. So therefore, this equation makes sense. Sum of the pH of solution is 14. If I ask pH of a solution is 10, what is the pH of solution? 14 minus 10 is 4. So if I give you pOH value of 12, pH value is equal to 2. So we can know pH of aqueous solution. We can easily calculate pOH or vice versa. Let's do more examples. I'm going to list some of the values of common materials. The battery acid, lead battery acid, pH is 0.5, which is very strong. Notice that gastric juice is also acidic. It's between 1.0 to 3.0. Lemon juice is acidic, 2.2 to 2.4. Vinegar is 2.4 to 3.4. Tomato juice is 4.0 to 4.4. Carbonated beverages, 4.0 to 5.0. Carbonic acid is acid. When carbon dioxide dissolved in water, produces slightly acidic. Even the black coffee is acidic, slightly acidic, 5.0 to 5.1. Urine is also acidic. And in extreme cases, it's slightly basic. It's more acidic. Rain is unpolluted, 8.2, 6.2, because of the carbon dioxide in air can produce. When sulfur dioxide is produced from burning sulfur containing coal, the rain water could have even higher acidity or lower pH than 6.2. Milk is also slightly acidic. On the right side of the table are the basic materials. On the left side, you have the acidic materials and their pH. Saliva is slightly acidic to more basic, 7.5. Pure water is 7 because ionization constant is Kw is 1 times 10 to the negative 14. Therefore, 1 times negative 7 times 1 times negative 7. pOH is also 7. pH is also 7. Blood has basic pH because of the bicarbonate buffers, slightly basic. Bile is acidic to neutral. Bile is secreted from gallbladder to facilitate digestion of fatty acid foods. Fats are emulsified by bile acids, which are slightly acidic. Pancreatic fluids are also 7.8 to slightly basic. Seawater is basic. The carbon dioxide is dissolved in water and produce bicarbonate. Bicarbonate causes it to be basic. Soap is also basic. It contains certain amount of bases that are added to vegetable oils. Some bases react with hydroxide to produce sodium salt of fatty acids, which are basic. Milk of magnesia has 10.5. Milk of magnesia is taken to reduce the acidity, stomach acidity. Therefore, it's used as antacid. Milk of magnesia is magnesium hydroxide. Household ammonia has 11.7. Lye is sodium hydroxide. It has the highest pH. Starting from battery acid to lye, which is sodium hydroxide solution, which has the highest pH value. Now we're going to look into acid-base titrations, which are used to quantify, measure amount of acid and bases in a solution. If you have a basic solution, we titrate it with acid solution to the neutralization point and find out quantities of volume of the acids and base, and knowing the molarity of the acid or the base, you can calculate the unknown molarity of other acid or base. Titration using a burette and conical flask is a procedure in which solute is in an unknown concentration, solute in mainly acidic or basic solution, react according to stoichiometric ratio as given in a chemical reaction. Using this chemical reaction, you can calculate the concentration of the unknown solution. In this chapter, we are concerned with titrations in which we use as an acid. Titrations are general procedure. It could be any chemical reaction, reacting with each other. So in acid bases, acid or base of unknown concentration can be determined using another acid or base solution to complete the neutralization reaction. Let us look at examples of titration. And titration of acid base must meet these requirements. So we must know the equation for the reaction. If sodium hydroxide and HCl is the acid base, and we have to know the balance equation. The reaction must be rapid and complete. Normally these solution reaction take place quickly, and therefore rapid and complete is satisfied. So equivalence point is where the two reagents, acid and base, have combined exactly. Neutral point is called, of acid-base reaction is called the equivalence point. To find out the equivalence point, we use acid-base indicators. So we must have an accurate measurement of each amount of reactant, volumetric flash, measure accurate amount of volumes of reactants. The indicators are used to identify the equivalence point. So some indicators change color based on the pH changes. If you look at this chart, thymol blue, first one, changes color from pH of 1 to 2.7. Congo red changes blue color at around 3 pH of 3 to about to red color. So there's a range of indicators that we have discovered to cover most of the pH ranges. So if your acid-base titration at equivalence point, pH is 2, methyl red, thymol blue is the best indicator. If your titration changes color around 8 and 9, slightly basic, phenolphthalein is the one that being used, 8 to 7. So you can pick up a indicator which change the color at the pH of equivalence point. So you can successfully measure equivalence point and the concentrations of acids and bases using volumetric glassware, burette, and the conical flash. As an example, let us use sulfuric acid, 0.8108 molar. Determine the concentration of sodium hydroxide solution. We're going to do a titration of a known volume of sodium hydroxide solution, and we titrate it with unknown sodium hydroxide solution is titrated with sulfuric acid with known concentration of sulfuric acid. So when at the equivalence point, we can calculate the number of milliliters of sodium hydroxide solution, and we can calculate the molarity of the sodium hydroxide solution. The balance equation is given here. 2 moles of sodium hydroxide react with 1 mole. So that is the criteria that we use. 2 moles of sodium hydroxide is equal to 1 mole of sulfuric acid. The reaction between hydronium ion is always rapid and complete. They take place quickly. We use the acid-base indicator as shown in the previous picture, different pHs, or pH meter. pH meter also shows change in pH, and we can calculate from the pH meter, if you graph pH versus volume of reactants, you can find the change in pH at the equivalence point, either using an indicator or pH meter. We use volumetric glassware to accurately measure burettes and conical flasks to measure volumes of the acids and the base that are used in the titration. The average value of 3 trials when you use 25 milliliters of sulfuric acid. You can see trial 1, we start with same amount of sulfuric acid. And there's an experimental uncertainty. We talked about uncertainties in the second decimal place. So average of these three, 33.48 is 33.48 average. Average value of these 3 trials for volume of sodium hydroxide. So using that, we can calculate number of molarity of the sodium hydroxide solution as shown in the following calculation. You start with, to calculate moles of sodium hydroxide divided by liters of sodium hydroxide. We start with 0.08 sulfuric acid. We converted it to volume of sodium hydroxide and volume of sulfuric acid and mole conversion ratio. We use 0.61 moles of sodium hydroxide is equal to 1 mole of 1 liter of sodium hydroxide. Therefore, molarity is 0.161. So unknown sodium hydroxide solution has the molarity of 0.161. That's what we are looking for. That's how you calculate concentration of unknown solution used in the titration. In here, the sodium hydroxide solution. Now we're going to talk about buffers. Especially they are called pH buffers. They resist changes in buffers, are able to resist changes in pH. When acid or base are added to the solution containing the buffer solution. A buffer is an acid or base shock absorber. That means when you add an acid, pH is decreased of the solution, or base is added to the buffer solution. pH supposed to increase the base, supposed to increase the pH of solution. However, buffer solution maintain the pH at the original level. Therefore, act as a shock absorber for pH changes. The pH buffer is normally called a buffer. Buffer means pH. The most common buffers consist of approximately equal molar amounts of weak acid and the salt of a weak acid. The weak acid, for example, acetic acid is weak acid. salt of a weak acid is sodium acetate. It is a combination of weak acid and conjugate base. This is equal amount, equal molar concentration. So this is equal to weak acid and a salt of its conjugate base. So how do you make a buffer? Pick up a weak acid and conjugate salt of that acid. So for example, if you take 1 mole of acetic acid, 1 mole of sodium acetate solution, this is the weak acid conjugate base combination. Then you produce an acetate buffer. How does the buffer absorb pH changes? For example, acetate buffer, acetic acid, the equilibrium in the acetate buffer is acetic acid react with water to produce acetate ion. So weak acid and conjugate base, acetic acid. So if you add acid, acetate ion absorb the hydronium ion, acid coming from acid, and equilibrium shift to right side. If you add a base, it will neutralize OH from the base, producing more acetate ion. So this is back and forth. It can shift and maintain the pH. How does an acetate buffer resist changes in pH? If a strong acid HCl is added, the hydronium ion produced react with acetate ion and are removed from solution. That's what I said before. This is the reaction for removing acid from the hydronium ion from the solution. If you add a base, acetic acid will react with hydroxide ion and remove it from the solution. Therefore, it maintains the pH of the solution through the common ion. Common ion is acetate ion for this reaction. There are other examples of pH buffers. The effect of a buffer can be quite dramatic. Consider the phosphate buffer. Like acetate buffer, phosphate is phosphoric acid and its conjugate base, sodium dihydrogen phosphate. In this phosphate buffer, weak acid is sodium hydrogen phosphate. That one has acidic hydrogen. And conjugate base is sodium hydrogen phosphate. Now it has one less hydrogen proton, H2, become Na2, HPO4. Combination of these salts in water in concentration of 0.1 produce strong acid, strong base. The pH changes by only 0.09. So these buffers, phosphate buffers, only change pH by 0.09 units. So if you phosphate buffer, pH is 7.21. We're going to talk about how to calculate the pH of a buffer in a minute. So when you add HCl, 0.010, it only changes 7.21 to 7.12. If you add hydroxide ion 0.01, it only changes 7.2 to 7.30. It's a change only 0.9 units. Therefore, it maintains the pH within the 7 range. The buffer pH. How do you know the pH of a buffer? If you mix equal amount of weak acid and salt, its conjugate base, salt as its conjugate base, pH is equal to pK value of weak acid. K-sub-A value for acetic acid is known, 1.8 10 to the negative 5. So we can calculate the pK value from the K-sub-A value. 9.14 pK value of boric acid. We are not talking about acetate buffer, boric acid buffer. Boric acid is BH3BO3. There's another buffer called boric buffer. Sodium dihydrogen borate is the conjugate base. If you have equal concentration of these two acids and the conjugate base, pK of the solution is 9.14. So there are different buffers like indicates for with different pH, different buffers for particular buffer regions. The capacity to absorb hydronium ion and hydroxide ion is called the buffer capacity. It depends on the pH and its concentration, buffer capacity. So the closer the pH of a buffer to the pK value of the weak acid, the more symmetric the buffer capacity, either acidic or basic shift are symmetric, meaning the buffer can resist pH change with added acid or base. So the solution has to have the pH of closer to the pK value of the weak acid. Greater the concentration of weak acid and the conjugate base. In previous example, boric acid and sodium borate, greater the molarity, they are equal concentration of weak acid and the conjugate base. More the concentration, greater the buffer capacity. Blood also keep the pH around 7.4 using blood buffers. Blood uses what we call carbonate buffer. Carbonic acid and its conjugate base. Weak acid is a carbonic acid. Conjugate base is a bicarbonate ion. So pKa value of carbonic acid is close to 7.4. An average, any change greater than 0.1 unit in either can cause illness. pH changes of blood is important factor that need to be maintained to become normal, healthy person. If changes in 0.1 of pH change of 0.01, that cause illness. To maintain pH, the body uses 3 buffer systems, mainly carbonate buffer, phosphate buffer. Weak acid is H2PO4 negative, sodium H2PO4. Conjugate base of that one is sodium disodium hydrogen phosphate, sodium hydrogen phosphate. There are other protein molecules that are used as weak acid and conjugate base acids based on proteins. We are not going to talk about that in this chapter. Now there's an important equation called Henderson-Hasselbalch equation that can be used to calculate the pH of a buffer solution. The pH of a buffer solution given, and the pK of the weak acid is given. The concentration of weak acid and its conjugates is given. We can derive an equation, Henderson-Hasselbalch equation, based on dissociation equilibrium of acid and its conjugate base. Acid is HA, conjugate base is negative, A negative. So we can take the logarithm of this equation and take negative signs. Minus log K sub A is equal to minus log K sub A. And we can find out taking the logarithm. So taking logarithm, you don't need to derive this equation. This is how it's calculated. Log K A is converted to minus log K sub A is equal to minus log hydrogen ion concentration, minus log conjugate base divided by weak acid. So if you take minus log K sub A is pKa value, minus log hydrogen ion concentration, we discussed about this, is equal to pH. The Henderson-Hasselbalch equation is pKa is equal to pH. The most important thing is pH. Therefore, we rearrange to give pH of a acid base, weak acid conjugate base buffer by this equation. Henderson-Hasselbalch equation is pH is equal to pKa plus log conjugate concentration of conjugate acid divided by weak acid. So we can calculate the pH of a solution knowing the concentration of conjugate base A minus or conjugate weak acid HA using this equation. So, for example, pH of phosphate buffer. Conjugate weak acid is 1 mole. Weak acid is sodium dihydrogen phosphate. Conjugate base is sodium hydrogen phosphate. Since we dissolve in 1 liter of solution, both are in 1 liter, concentration of weak acid is 1.0. Conjugate is 0.5. We plug in the equation, these values. On the pH here, 7.1 comes from pKa value of pKa value of sodium dihydrogen phosphate is 7.21. Log 0.50 comes from conjugate base concentration. 1.0 comes from weak acid concentration. So that pH of the buffer is made out of these compositions is 6.91. Can you see that you can change the ratio of hydrogen, weak acid, and conjugate base and change the pH of a buffer from pKa value? If the concentration of weak acid and the conjugate base are equal, pKa value is same as pH of the buffer solution. The original laboratory buffers used in biochemical studies were made from simple acid bases like acid buffer, phosphoric acid, citric acid, and conjugate bases. However, many of these have several limitations. They escape from the cell solution. They often change pH too much if the solution is diluted or temperature is changed. They are sensitive to lower dilutions and high temperatures, different temperatures. They often permeate cells in the nearby solution, thereby permeate the cells in the solution, changing the chemistry of the interior of the cell. Therefore, any good develop a series of buffer that consist of pseudoions and molecules that do not rapidly permeate cell membranes. So avoid drawbacks of simple buffer. They come up with these two buffers called TRIS and TES. The names are given. So they are used in biochemical solutions when you study living cells. These buffers are much more resistant to pH change of the solution. So we have gone over chapter 8, acid bases. Definition of acid bases. Weak acids, strong acid, weak bases, strong bases, how we identify. And we also talk about K sub A values, pK sub A values, pK sub A values. Kw, 1 times 10 to the negative 14, ion product of water. And pH of the water solution, pOH of the, as also pOH of the water solution. Then we talked about titrations. And finally, we done some concept involving pH buffers. So how to calculate pH of a buffer using Henderson-Hasselbalch equation. Now we need to go through some problems. I'm going to cover chapter 7 next class period. And I'm going to record the chapter 8 questions and answers. And you can listen to it before you take the test next week. Okay? So we'll see you on Thursday. All right?